transient voltage surge is one possible cause. When a furnace turns off, the inrush current of the motor can cause a momentary voltage drop on the neutral line, resulting in a voltage surge in the other legs of the circuit. This surge could cause the incandescent light to flash. Inductive kickback is another possibility. The inductive load of the furnace motor can generate a voltage spike when the power is turned off, which can cause the neutral line to temporarily reverse polarity. This could cause the incandescent light to briefly brighten before resuming normal brightness. Loose or corroded connections could also be the culprit. A loose or corroded connection in the neutral circuit could create a high resistance path, causing a voltage drop that could lead to the observed behavior. A wiring fault is another possibility. A wiring fault, such as a reversed polarity or a short circuit, could also cause the neutral line to become compromised and result in voltage fluctuations. Recommended actions include inspecting the wiring. Check the wiring connections at the furnace light fixture and panel for any loose or corroded connections. Ensure the neutral wires are properly terminated and securely fastened. Another recommended action is to measure the voltage. Use a voltmeter to measure the voltage on the neutral line of the circuit while the furnace is running and turned off. Look for any significant voltage drops or spikes. Replacing the light bulb is another step. If the voltage measurements are within normal limits, consider replacing the incandescent light bulb with a new one. Incandescent bulbs are more susceptible to voltage fluctuations than other types of bulbs. Consider grounding as another option. If the above steps do not resolve the issue, consider adding a ground wire to the circuit. A ground wire can help dissipate voltage spikes and prevent them from affecting the neutral line. Also consider multiple circuits. If the basement light is on a different circuit than the furnace, the issue may be caused by an interaction between the two circuits. Check the circuit breakers or fuses for both circuits. Note any other appliances or devices connected to the same circuit as the furnace and light. Excessive current draw from other appliances could contribute to voltage fluctuations. The 2017 National Electrical Code, or NEC, does not specifically address this exact scenario but provides general guidance on wiring methods, grounding, and of current protection that are relevant to troubleshooting such issues. Several sections of the NEC could be relevant. Firstly, Article 200 covers the use and identification of grounded conductors. It requires that the neutral conductor be properly identified and connected to the grounding electrode system. Secondly, Article 210 covers branch circuits. This article provides requirements for the types of branch circuits allowed in dwellings, the permissible loads, and the overcurrent protection requirement. Thirdly, Article 250 covers grounding and bonding. This is perhaps the most relevant article, as it provides detailed requirements for grounding and bonding electrical systems to ensure a low impedance path for fault current. It covers the grounding electrode system, equipment grounding conductors, and bonding of metal enclosures and equipment. Fourthly, Article 300 covers general wiring methods. This article provides requirements for how conductors must be installed, supported, and protected. It also covers issues such as conductor fill in conduit and the use of approved fittings. Fifthly, Article 310 covers conductors for general wiring. This article provides requirements for the types of conductors that can be used, their ampacity, and their installation requirements. This article might be relevant if undersized conductors are suspected to be contributing to voltage drops. Sixthly, Article 430 covers motors, motor circuits, and controllers. This article provides requirements for the protection of motors and motor circuits, including overcurrent protection, overload protection, and disconnecting means. Since the furnace motor is involved, this article is particularly relevant. In the context of the original problem, here's how these NEC articles might apply. Regarding Article 200, ensure the neutral conductor is properly identified and connected. Check that the neutral conductor is properly connected to the grounding electrode system at the service entrance. A loose or corroded connection here could cause voltage fluctuations. As for Article 210, verify the branch circuits are correctly configured. Check that the lighting and furnace are on appropriately sized and protected branch circuits. Overloaded circuits can cause voltage drops. With Article 250, inspect the grounding and bonding system. Ensure that the grounding electrode system is intact and that all metal enclosures are properly bonded. A poor grounding system can exacerbate voltage fluctuations and increase the risk of electrical shock. In terms of Article 300, review the wiring methods. Check that all wiring is properly installed and supported, and that conductors are protected from physical damage. Damaged or improperly installed wiring can cause a variety of problems, including voltage drops and short circuits. Considering Article 310, confirm the conductor sizes are adequate. Verify that the conductors are sized appropriately for the load they are carrying. Undersized conductors can cause voltage drops, especially when the furnace motor starts. Regarding Article 430, assess the motor circuit protection. Ensure that the furnace motor is properly protected against overcurrent and overload conditions. Problems with the motor circuit can cause voltage fluctuations on other circuits. Several specific NEC sections might be helpful. NEC Section 250.24c discusses continuity of grounded conductor. This section requires the grounded conductor to be continuous and not switchable, which is relevant to ensuring a stable neutral connection. NEC Section 250.50 covers grounding electrode system. This section specifies the requirements for the grounding electrode system, including the types of electrodes that are permitted and how they must be connected. NEC Section 250.166 covers sizing the grounding electrode conductor. This section provides the requirements for sizing the grounding electrode conductor, which is important for ensuring that the grounding system can effectively carry fault current. NEC Section 300.11 covers securing and supporting wiring. This section requires wiring to be securely fastened in place, which can help prevent loose connections and physical damage. NEC Section 310.15 covers ampacity of conductors. This section provides tables and guidelines for determining the ampacity of conductors, which is important for ensuring that conductors are not overloaded. NEC Section 430.52 covers motor overcurrent protection. This section specifies the requirements for overcurrent protection of motors, which is important for protecting the motor and the circuit from damage. When troubleshooting the incandescent light flashing issue, consider these steps. Firstly, perform a visual inspection. Check for any obvious signs of damage or loose connections at the light fixture, furnace, and electrical panel. Secondly, measure voltage at the light fixture. Use a voltmeter to measure the voltage at the light fixture while the furnace is running and when it shuts off. Look for any significant voltage fluctuations. Thirdly, check the neutral connections. Inspect the neutral connections at the light fixture, furnace, and electrical panel. Ensure that the connections are tight and free from corrosion. Fourthly, test the grounding system. Use a multimeter to test the continuity of the grounding system. Ensure that all metal enclosures are properly grounded. Fifthly, evaluate the circuit loading. Check the circuit breaker or fuse for the circuit to see if it is overloaded. Remove any unnecessary loads from the circuit. Sixthly, monitor the furnace operation. Observe the furnace while it is running and shutting off. Listen for any unusual noises or vibrations. Look for any signs of overheating or arcing. By systematically checking these items and referencing the relevant NEC articles and sections, one can effectively troubleshoot and resolve the incandescent light flashing issue. It's important to remember that electrical work can be dangerous, so it's always best to consult with a qualified electrician if you're not comfortable performing the work yourself. Be aware of voltage drops and their potential causes and remedies. Voltage drop is the decrease of voltage along a conductor through which current is flowing. It's an important consideration in electrical systems to ensure that equipment receives the proper voltage for efficient and safe operation. Here's a breakdown of voltage drop, its causes, effects, and remedies. The causes of voltage drop are firstly, conductor resistance. All conductors have some level of resistance to the flow of current. The longer the conductor and the smaller its cross-sectional area or gauge, the higher the resistance. Secondly, current flow. The amount of current flowing through a conductor directly affects the voltage drop. Higher current results in a greater voltage drop. Thirdly, load impedance. The impedance of the load connected to the circuit also affects voltage drop. Loads with lower impedance draw more current, leading to a higher voltage drop. The effects of excessive voltage drop are firstly, reduced equipment performance. Equipment may not operate correctly or efficiently if the voltage supplied is too low. For example, motors may run slower or overheat, and lights may dim. Secondly, overheating. Excessive voltage drop can cause conductors and equipment to overheat, which can damage insulation and increase the risk of fire. Thirdly, equipment damage. Some equipment is sensitive to voltage variations and can be damaged by prolonged operation at reduced voltage. Fourthly, safety hazards. Low voltage can cause equipment to malfunction, creating safety hazards such as electrical shock or fire. Some remedies for voltage drop are firstly, increase conductor size. Using a larger conductor with a lower gauge reduces resistance and minimizes voltage drop. Refer to NEC tables, such as Table 310.15b16 for conductor ampacity and corresponding sizes. Secondly, shorten conductor length. Reducing the length of the conductor decreases the total resistance and voltage drop. This may involve relocating equipment or power sources. Thirdly, reduce current flow. Lowering the current flowing through the circuit reduces voltage drop. This can be achieved by reducing the load on the circuit or using more efficient equipment. Fourthly, improve connections. Ensure that all connections are clean, tight, and free from corrosion. Loose or corroded connections increase resistance and contribute to voltage drop. Fifthly, use multiple circuits. Distributing the load across multiple circuits reduces the current flowing through each circuit, minimizing voltage drop. Sixthly, increase supply voltage. Increasing the supply voltage can compensate for voltage drop, but this may require upgrading equipment and wiring to handle the higher voltage. Seventhly, use voltage regulators or stabilizers. These devices maintain a constant output voltage, compensating for variations in the input voltage. Here are some calculations regarding voltage drop. The basic formula for voltage drop is voltage drop equals current times resistance, or volts equals amps times ohms. The percentage voltage drop is calculated as percentage voltage drop equals voltage drop divided by source voltage times 100. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. The NEC provides guidelines and tables for calculating voltage drop and selecting appropriate conductor sizes. Section 215.2 AM provides a recommendation for maximum voltage drop on feeder conductors. Section 210.19 AM provides a recommendation for maximum voltage drop on branch circuit conductors. Table 8 in Chapter 9 provides conductor properties, including resistance per foot. Here is an example calculation. Consider a 120 volt circuit with a 100-foot run of 12 American wire gauge copper wire carrying 15 amps. The resistance of 12 American wire gauge copper wire is approximately 1.98 ohms per 1000 feet, or 0.198 ohms per foot. The total resistance for a 200-foot loop, there and back, is 200 feet times 0.198 ohms per foot, which equals 0.396 ohms. The voltage drop is 15 amps times 0.396 ohms, which equals 5.94 volts. The percentage voltage drop is 5.94 volts divided by 120 volts times 100, which equals 4.95%. In this example, the voltage drop is close to the recommended limit for branch circuits. To reduce the voltage drop, one could use a larger conductor size, such as 10 American wire gauge. Remember that voltage drop calculations should consider the entire circuit, including both the supply and return conductors. Always consult the NEC and local electrical codes for specific requirements and recommendations.